My name is Dr. Paul Houle, and in this radon program, I'm going to present to you a brief introduction to the radon issues, which will include what I am going to call a contemporary historical review of the radon issue. During this program, there will be a set of visuals I'll be using, and you can see the first visual here. And you should turn to that portion of your text at this point so that visual is in front of you. And then you should follow along with these visuals as I present them. You have the full set just as I have here in front of me. That way, if you want to make any notes during the program, you can make them right there on the visuals. So let's begin with the brief history of the radon issue. As early as the late 1900s, with the advent of the discovery of radioactivity, radon had been known to be a radioactive gas. And by 1950, 1960, it was well accepted within the scientific community that this radioactive gas, if inhaled, which was done by typically uranium miners, tin miners, mini miners who were digging into the ground, would induce lung cancers beyond what would normally be found in the population. That is, radon gas was considered to be a health hazard even in the 50s and 60s. And even in that time, in the 1950s, 1960s, some houses had been discovered that were built from materials that housed a lot of uranium, or a significant amount of uranium, such that that uranium, when it radioactively decays, would produce radon, which is a gas, and that would come out of the building materials and go into the building. And then the occupants of the building, of course, would be breathing that gas. Now, that happened in the vicinity of uranium mines predominantly. When you dig out a mine and you're searching for the uranium ore, you pull out a lot of material that you're not going to use, and that is called the mine tailings. And some of those tailings, of course, can be used to backfill the mine when the mine is mined out, when there's no more valuable ore left. And some of the mill tailings can be used in construction, and that's what had happened. And so some of these construction materials actually had more uranium in them than you might typically find. And then that uranium produces radon, and then the radon comes into the home. So by the 50s and 60s, as a construction material problem, the radon issue was fairly well founded. But I'm not going to define that as the beginning of the contemporary radon problem. I'm going to define the beginning of the contemporary radon problem as you see here in this visual, where I say the U.S. became aware in the fall of 1984. Now, I'm going to claim that as the beginning because up until this time, it was not known, to many people certainly, that radon could be a gas in a home even though the construction materials of the home were free of any radioactive material. And the way it started was an individual named Stanley Watrous, who lives in Pennsylvania and at that time was working at the Limerick nuclear power plant prior to the power plant being brought online. And as you may know, many of these power plants, in fact all power plants, all nuclear power plants anyway, are required to have monitors at all the exits so that when the workers leave the plant, they can pass through a radioactive monitor to determine how much radioactive material might be on their persons. And typically, you find none. You find very, very, very minuscule amounts of radiation attached to people's clothing. Well, Stanley Watrous, anytime he left one building at that plant facility to go to another building, he would have to go out one of the exit doors and pass through the monitors, and he would be setting the monitors off. So even if he was only going to deliver a message to the next building, he would set the monitor off, have to go through a decontamination process, which would take several hours, and even before he could get his message delivered. Well, this happened on numerous occasions. And Stan Watrous got quite concerned about the issue, wondering where is this radioactive material coming from. The nuclear facility was not able to determine that it was coming from the nuclear plant itself. So one morning, on the way into work, and this is where I call the December '84 event, the beginning of the radon issue, On his way into work, he parked his vehicle, and then instead of walking to his normal place of work at the Limerick power plant, he went to one of the exit doors and stood in the monitors and set them off again. He convinced the power plant to send some of its people over to his home, where they detected radon gas in the home. That was then confirmed by the Pennsylvania DER that in fact there was a high concentration of radon gas. And as you can see in the visual, the concentration was over 2,000 picocuries per liter. Now I'm going to talk about this unit of a picocurie per liter briefly in a minute, but that's the unit that we use to measure radon gas concentrations. And just to give you a handle on how high that value is, currently the EPA says that if your home has more than 4 picocuries per liter of radon in it, you ought to do something about it to get it below that value. So here it was, the Watrous home with more than 2,000 units of radon gas in it. Now, it wasn't coming from the building materials, and so how was it getting into the house? Well, if you go beneath the surface of the earth, and you don't have to go far, I'm not talking a mile down into the ground, but really just a few feet, you'll find uranium and some other materials fairly uniformly distributed across the ground. Now, I'm not suggesting that it is in fact uniform everywhere. Some areas of the ground will have a little more uranium than others, etc. But there is some uranium spread throughout the planet. Apparently at the beginning of when the planet was created some 4 billion years ago, give or take a few minutes, most of the materials were pretty uniformly distributed. Obviously, some regions have a little more than others, but there is some uranium just about everywhere. This uranium is radioactive, and that breaks down eventually and becomes radon gas. So here you have, beneath the soil, this radon gas mixed in with all the other soil gases that are down there. And this radon gas, because the soil pressure is a little bit larger, not a lot, but a little bit larger than the atmospheric pressure above it, this radon gas percolates up through the soil and gets vented into the atmosphere. And of course the atmosphere is a pretty large volume, so that dilutes the radon gas concentration to relatively low values. If, however, you put a house on top of a given location and there isn't too much ventilation in the house, then that radon gas can percolate up into the house and be trapped. And that's how the gas had been getting into the Watrous home. And that really was the event that made radon gas a contemporary problem in the United States. And currently, and for quite some time now, the EPA, as you see here, has estimated that 1 out of every 15 homes in the United States has elevated radon levels. And what they mean by that are levels greater than 4 picocuries per liter, wherein it's recommended that the home be treated in such a way as to lower that radon concentration to values less than 4. We became involved in this issue shortly after December 1984, and one of the very first things we did was to execute a library search. And with the advent of automation, it was relatively easy, frankly, to search literally thousands of journals, magazines, searching for articles on the radon issue. And we discovered, as you see here, some just points of interest. Sweden, by that time, had determined that 40% of its cancer deaths are radon related. Mexico found high concentrations of radon in homes and attributed those concentrations to the building materials, which had been made out of volcanic rock. And apparently volcanic rock has a significantly greater amount of uranium and radium in it than other kinds of rock. Homes had been built out of this kind of material, and the radon gas had been seeping into the homes from the building materials. I have a sketch here taken from one of the EPA manuals that gives you some idea of how the radon gas can get into a house. Predominantly, you should remember that it's a soil gas. You should not expect that radon will enter a house through windows and doorways, because that's the outside atmosphere, and the outside atmosphere is so large that it has already diluted the radon gas to extremely low values. But as a soil gas, you can see here that it'll come up through expansion joints in concrete slabs, cracks in concrete slabs, utility openings, through sump holes, etc. And you also see here that, where it's labeled E, that it can get in through the water as well. If your house is on a well, then you're taking water from underneath the ground, and radon is somewhat soluble in water, and so it dissolves into the water. And then you bring the water into the house when you turn the shower or the faucet on, and if you agitate the water a little bit, the radon will come out of the water, and then it becomes a radon and air problem again. And there is also some information indicating that there is a health risk from drinking water with high concentrations of radon in the water. So these are the modes by which the radon can get into a building. But I think predominantly the thing you should remember at this point is that it is a soil gas. It comes up from the ground and gets into the house, as you see indicated here. Continuing on with that library search, we also discovered these countries found concentrations of radon higher in homes than what you would typically get outside. And in fact, there was no country that we investigated, that we were able to investigate, which had no radon problem. In fact, every country that we investigated, to put this in a positive light, every country that we investigated has admitted to a radon problem in that country. This means that it's not a problem in New Jersey or just Pennsylvania, or Pennsylvania, New Jersey, and Maine, and Florida, and Ohio, but in fact, it is a planet-wide problem. It's not a problem in given locations alone. Now, it is true that some locations are more prone to the radon problem than others because those locations will have more uranium in the ground than others. And remember, you have to have some uranium at some point in order for that to decay down and become radon. And I'll make a few more comments about radioactivity in just a second. Now, I've mentioned that outside the concentrations are relatively low. And here we have a value. The outdoor average typically will run around 0.4 picocuries per liter. 0.4, 0.5 picocuries per liter, maybe even a little less than 0.4. And in fact, there are fluctuations in those values from daytime through nighttime values. The concentration outside goes up and down and up and down, but on the average runs around 0.4 picocuries per liter. Now, this is a good point to spend a minute describing radioactive decay in light of that unit that we're using. We're using the unit of the picocurie per liter, and that is a very common unit of measurement when we're talking about radioactivity. And all I mean by radioactivity is this: if you take an atom, and there's a whole slew of atoms, of course, there's more than 100 different kinds of atoms that you can get, an array of elements. And if you take one of these atoms and you just leave it there, just let it sit there, if in a reasonable amount of time it explodes all by itself, we call that a radioactive atom. A lot of atoms you can put here on the shelf and leave them there forever, and they will never explode. Hydrogen, helium, nitrogen, etc. There's a whole slew of atoms which are not radioactive. But there are some that are radioactive. And if you take, for example, take a uranium atom and you sit it on the shelf, well, after a little bit of time, that uranium atom will explode. And it will give off fragments from its explosion in different directions, and it will leave behind a little bit of material, which is another kind of atom. And that other kind of atom is called a daughter product from uranium, or a daughter of uranium. Uranium would then be the parent of that daughter. And then that daughter, in the case of uranium, that daughter of uranium is also radioactive, so it explodes, given a little bit of time. And then its daughter also explodes, etc., until eventually what we discover is the atom that's produced is radon. So uranium decays down into radon at some point. And radon is a gas. So if you have uranium underground, which is a solid, and it's decaying down into other solids and other solids and other solids, and eventually becomes radon, but radon is a gas, and then that radon percolates up into the atmosphere as I've described. Now radon is radioactive too, and of course that's what makes it a health hazard. If you're inhaling radon, and it explodes while it's in your lungs, and believe me, if you're inhaling some radon, some of it will explode while it's in your lungs, you can imagine that some damage can occur to your lungs. And the kinds of damage that we're interested here, in this case, is the kind of damage that induces lung cancers. Now, 1 picocurie per liter, as you see here in this visual, is 2.2 radioactive decays per minute in a 1 liter volume. So here I've got a 1 liter bottle, and it's just a liter of seltzer water that I took from home this morning. Give you an idea of the physical size. A liter is about a quart. It's just a little bit different from a quart, but close to a quart. And if somehow I could look into here and see the radon, of course radon's invisible, you can't see it. It's odorless, tasteless. In fact, none of the human senses can detect radon, which is a problem with it, as you might expect. But if I could look into here in this 1 liter bottle, and if I could see, on the average, 2.2 atoms of radon exploding, decaying, in 1 minute, then I would say there were 2.2 disintegrations in this 1 liter in that 1 minute. 2.2 decays per minute in a liter. And so that would be 1 picocurie per liter of radon concentration in here. Suppose I had, let's pick something neat. Say I had 5 picocuries per liter in here. That would mean 5 picocuries in this 1 liter. Well, 5 times 2.2 is 11. So if I had 5 picocuries per liter in this liter, if I were to look in there, every minute I would expect to see 11 disintegrations during that 1 minute. So the higher this number is, the higher the number of picocuries per liter, the more the number of decays are that you will see in 1 minute. Now the working level, that's equivalent to 200 picocuries per liter. Now that's another relatively common measurement in the radon issue, and in fact in any radioactive issue. And on the average, and I only mean on an average, there are a lot of parameters that impact this value, but on the average, if you have instruments that measure in terms of working levels, then you should remember that 1 working level is roughly 200 picocuries per liter, roughly. So I indicate that with the word approximately. Now, I think we can detect, even though we can't see radiation, we can detect some radiation. Remember, if you take a look at a radioactive atom, after a little bit of time, it's going to explode. And when it explodes, it leaves behind another atom, and some fragments have gone off in different directions. Now we can detect those fragments because we're clever. We've developed certain instruments which allow us to detect those kinds of fragments. And even here in the studio, there is some radioactive fragments passing through the building and passing through this space in which I'm standing. And we call that background radiation. And we can use what many of you are familiar with or have seen anyway, are Geiger counters. This is the detector right here. And I'm just going to turn it on. And I think you can hear the background radiation. Every click that you hear is one of those fragments passing into this detector. and this detector picks it up. Now, it's not a lot, so background radiation is typically quite small. But to help you sense radioactivity, I've brought some sources of radioactivity which give off lots of particles, lots of fragments. That is, there's lots of radioactive atoms in here, and many of them are exploding every instant. And I think you can tell that that's a lot more than just your background radiation. Anyway, this is one of the kinds of devices that you can use to detect radioactive material. This is a good point for you to stop, and you'll see on the very next page there's a brief list of questions that I would like you to work through. Now, work through those questions, and after you've worked through all of them, check your answers with the answers given in the back of the book and see how you've made out in that regard. And then return to the video at this point. I hope you made out well with those questions and answers, and certainly one comment I would like to make is when you're through with this program, if you have any questions remaining in your mind, please feel free to give us a call. We'll be happy to work with you through whatever questions you might have. Continuing on with this overview of the radon issue, the EPA in the United States was given a series of responsibilities in dealing with this issue, two of which were to identify those geographic areas which might be more prone to radon than others, and two, to establish guidelines by which we might be able to gain a handle on the radon issue, which they have since done. In particular, I've already made reference to one, which is the so-called action limit of 4 picocuries per liter. That is, if the radon concentration in a home is greater than 4, the EPA recommends that the home be mitigated to get the concentration down below that value. So they have that guideline, plus they have an array of guidelines beyond that, and I think the EPA has certainly met its responsibilities on these issues. In talking about the geographic areas, the EPA has also gone quite far with this issue, and they have done a very intensive study of the United States, and you see here what I'm calling the EPA map of radon zones. Actually, that's what they call it, the EPA map of radon zones. And it's divided into 3 areas by counties across the entire United States. And you'll notice there's a Zone 1, Zone 2, and Zone 3. Now, all this means is for Zone 1, the concentrations are greater than 4 picocuries per liter. Now, let me clarify that. This is a map of radon zones, of potential radon zones. In other words, they're expecting that in Zone 1, the dark regions here that you see here, which pass through Pennsylvania, New Jersey, and pass up through Maine, for example, that in Zone 1, it's expected that if you measured all the homes in those regions of Zone 1, that the concentration average would be greater than 4 picocuries per liter. They don't know that that's the case, but that's their expectation. And they did a very large study to come up with this map. Zone 2, they expect the concentrations to run between 2 and 4 picocuries per liter, and you can see that's the lighter shaded areas here, down in through this region here. And Zone 3, where there's no shading at all, those concentrations are expected to be between 0 and 2 picocuries per liter. And of course, we have the other outlying states outside of the continent itself depicted here and here. Now, this shows that the radon concentrations are going to be bigger problems in some regions than in other regions. It's important, however, for us not to fool ourselves to think that, for example, suppose you lived in southern Texas, which would be a Zone 3 area. It's important not to think that, well, because I live in a Zone 3 area, therefore I don't have to worry about the radon problem. The only way to tell if you have a radon problem is to test for it. That is the only way you're going to be able to know. But clearly, some regions are more prone to the problem than others. There are other maps available, and I want to show you one or two more of them, simply because they're built a little differently in each case. Here's one published by the Pennsylvania DER. Now, this one is based on actual measurements in homes. It's not a potential radon map, it's an actual radon map, and you can see it's done by counties. And the more hash marks you have, the higher the radon concentration. In fact, this region in here, which has a lot of hash marks, you see, their average value for radon in the measurements in those counties run between 10 to 20. In the regions with just one hash mark, they look a little lighter in their shading. The average runs between 4 and 10, and those with just vertical stripes are between 0 and 4. Now, the blank ones, please note, the blank counties simply indicate that there's not enough data upon which to make a judgment. But you'll notice that anywhere in this particular state, the average concentration is not 0. It's always something. And you can easily have a home in a county out here, for example, where the concentration average across many homes that have been measured is between, let's say, 4 to 10. It's quite possible to have a home with a concentration that's 50 or 100 or 200. There will be anomalous cases expected in every county. Again, I want to underline the thought that the only way you're going to be able to tell if you have a radon problem in your home is, in fact, to test it. So this is a little bit different from the EPA map, because the EPA map is a prediction of what they expect in given regions based on a whole assortment of data and parameters. This is a depiction of the actual average radon concentrations that have been measured in Pennsylvania. Another map, and the last of this set, is for New Jersey, and I think, well, we can just barely make that out on this screen. But you can see it's what New Jersey calls its 1990-1991 radon potential map, which is still a very, very good map. And you'll see they have 3 tiers, a Tier 1, a Tier 2, and a Tier 3. And this map is interpreted differently from the other two, a little bit. In Tier 1, which is the darkest shading that you see here, in this region in here, Tier 1, in this region, the New Jersey DEPE expects more than 25% of the homes to come up with values greater than 4. So here they're giving a percentage of homes that they expect to come up with values greater than 4 picocuries per liter. In Tier 2, where they've labeled it moderate radon potential, there they expect between 5 and 24% of the homes to come up with radon concentrations greater than 4. And here in the counties with no shading, or rather these are municipalities, not counties, but municipalities, the concentration, let me rephrase that, the New Jersey DEPE expects that less than or equal to 4% of the homes in those counties will have radon concentrations greater than 4. So if you see any of these maps, be careful to understand how the map is constructed and, in fact, what the map is telling you. It is still possible to take a home out here where the county looks fairly clear of radon and have a home there with a concentration of 50, 100, 200 picocuries per liter. That is still quite possible. And again, I guess I've said it enough. The only way you're going to know, you got to test. Okay? So there's the New Jersey map. Okay. Again, following this page, you should see on the very next page another array of questions. And I'd like you to work through those questions, check the answers in the back, and return to the video at this point. Okay, I hope you did well with those questions and answers. And again, I want to repeat to you that if you have any further questions when you're done with this program, please feel free to give us a call. I want to talk now of how radon is detected. You'll see here on this visual there's a myriad number of ways. I've listed them as grab sampling, charcoal detectors, alpha tracks, continuous working level monitors, continuous radon gas monitors, and EPERMs, or electrets. I should probably rewrite that as electrets. But you'll see that I'm going to depict for you each one of these instruments and the periods over which they can make a measurement. Now, it would be nice to simply go into a home and immediately come up with the radon concentration in the home. And that's possible. You can go in with a grab sampling device that looks something like this, has a couple of hoses on it, and you connect it to a pump, just a little powered air pump. And what you do is you stick it in the home. It's easy to do. You just sit it there in the home. And you plug it into the pump, and you turn the pump on. And after a few minutes, this will fill up with, this will have the same air in it that the room has. And then you can take this back to the laboratory, and on a relatively sophisticated device, one of which I have right here, this would fit right on top of right on the device like this, and you can measure the radon concentration that's in that small cell. And what happens is as the radon in that cell explodes, the fragments are going to strike the wall of that cell. Let me get that back here. The fragments from the explosion strike the wall of the cell, and when they do strike the wall of the cell, light will be emitted and will come out through this front face. This device here will count up the number of light pieces it sees. Every time it sees a flash of light, it will know that one radon atom must have decayed. And so it counts up the number of atoms that have decayed, and by some fairly standard procedures, you can come up with a radon concentration from that. And that's called grab sampling, and you'll note it only takes a few minutes to do. And it comes up with an extremely accurate value for the radon concentration that was in the home at that particular instant. Now, the problem that we have with that, or at least that I have with that, is that when you, if you do that, you get an accurate value of the radon concentration at that particular time, but that is not an average value of the radon concentration in the home. In particular, I'll come back to this visual here in just a second. In particular, if I were to plot radon concentration here versus time, in one day, a radon concentration in a home can do this kind of thing. Goes all over the place. And it's extremely common. In fact, if I found a radon concentration that was straight all the way across for the whole day, I think there's something wrong with the measurement. And so the problem with taking a grab sample is that, suppose you take the grab sample at this point. Then you're going to say, well, the radon concentration at home is pretty low. And at that particular instant, you're absolutely right, it was low. But is it a health hazard? You're darn right it is, because the average is going to be much higher than that. We're looking for an average value. So we want to be careful that, that we not use grab samples to determine what the average value is in the home over a period of a few days. And in fact, one of the other guidelines that the EPA has published is that the minimum measurement period to measure radon is 2 days, 48 hours. That's the minimum measurement period. You have to make a measurement that averages the values over 2 days. So the grab sampling, while it can be extremely accurate, doesn't give you that average, and so it's not viable for coming up with that kind of average value. I suppose you could take a couple hundred grab samples, one right behind the other, over a period of 2 days, but that's pretty labor intensive and, excuse me, all in all pretty silly. There are other devices that take averages. I'll list the charcoal detector. I believe it is the most common detector in use. And I have a charcoal detector here, a sample of one. And all it is, principally, is a can filled with charcoal, held in place and a few other little things to help the canister work well. And all you have to do is you put this in the home, peel off the tape on the top, and you'll notice there's a little hole in the can. You stick this in the room that you want to test. You sit it, for example, if you want to test in a living room, you could set it on your coffee table, someplace where it won't be disturbed, but fundamentally you put it in the room that you want to test. And the air in the room slowly diffuses into the can, and as you know, charcoal absorbs almost everything. It absorbs organics, gases, and radon gas too. And so then this will be absorbing some of that radon gas. And after 2 days or longer, this runs usually between 2 and 7 days. You can deploy this in a home. So you can get an average value, something of an average value over those periods. And you send it back to the laboratory, and the laboratory will analyze the amount of radon gas that is in here and determine what the radon gas concentration must have been in the home during that deployment period. So the charcoal canister, as you see here, can be used from 2 to 7 days. You may also run across another kind of charcoal container. This is called a liquid scintillation vial. There's no liquid in it, but it's treated with a liquid later, which is why it's called a liquid scintillation vial. And you can see that it's filled with charcoal. I think you can see that. And in this particular case, it's about 15 grams of charcoal, but you'll see them from 4 grams of charcoal and up. And there's also a little bag in there which serves only to absorb water vapor. And in order to turn this on, you just decide which room you want to make the measurement in, open the cover, sit it there, wait the 2 to 7 days, take it out, put the cover back on, and you've got your radon sample in there. And that'll give you an average value over those days. Of course, you'll have to send it back to the laboratory for analysis. And every laboratory, of course, will have its own specific instructions. But pretty much what I showed you there is all you need to do. There's another kind of device called an alpha track device, and there are lots of companies that put out alpha track devices, and I have one here. And this one here, you could deploy it in a room, and for the number of days required or that you want to put it out for 7 days or whatever, or longer, excuse me, I said 7 days. You should put it out for a minimum of 30 days and out for as long as a year. And what happens is the gas seeps into here, and then when the radon explodes, if there's radon in the room, when it decays and gives off those fragments, I'm going to take this apart now. Do not do this if you're using one of these. This voids the measurement. But I want to show you the detector itself. And the detector is just this little piece of plastic. That's all it is. And when the radon decays, some fragments will come off in this direction and strike the plastic. And when they strike the plastic, they're actually going to leave a little scratch mark. Now, the scratch mark isn't visible to the human eye. And so this is treated much like photographic film when it's returned to the laboratory. And then they can count the scratches on it, the number of pits in the plastic. And they can tell from the number of pits how much radon this was exposed to on the average over the period, as indicated here, 30 days to a year. The more pits, the more radon it must have had. And so these things can be calibrated to identify radon concentrations. I make it sound so simple, but those laboratories are pretty sophisticated. I do have an image of what those pits look like. If you take a look at it, this is what that little plastic strip would look like if you blew it up and then wanted to count the pits. And so here you see this pretty significant number of pits on this particular plastic film. So that's what an alpha track would look like. Nice things about alpha tracks is that they are usable for long periods, from 30 days to a year. Charcoal detectors cannot typically be used much more than to get an average over about 7 or 8 days. Probably the most I've ever seen is a charcoal detector used for a period of 10 days. And that's pretty much the extent of it. There are weaknesses in those detectors beyond 10 days that make them not useful beyond that time. So alpha tracks have the advantage they can be used for very long averages. Continuous radon gas monitors. Well, you remember I told you you could, when you're taking a grab sample, you could go in and take a whole bunch of grab samples, one right after the other. But the problem with that is that it's a lot of manpower. It just seems like a silly thing to do. And so there is an automated device that does that. And I have one here. This one happens to be made by Pylon. And all you do, whoops, I'm going the wrong way. All you do is you put this cell in here, and you connect it to a pump, and there's a pump right in the device. And so all you have to do is connect it, take this hose, say, connected to the back, and there's a pump here, and you'll be able to hear this. And I'll turn this on. And we just give it a minute to warm up. And what this will do is pump air. It'll take, if this is in the room you're going to make the measurement, you leave one vent like this open. And so what it's going to do, it's going to pump air from the room through the cell and then out again. And so this will be constantly sampling the room air. And I can turn the pump on here. And I think you can hear that. And now there is air coming out. Yep. You can hear the pump vary through the, as I plug that. And so what this is doing is sampling the air in this room, in the studio. And on the front face here, if you could see it, it's actually depicting the number of counts per minute. I don't know if we can, oh, it says ready here. I gotta, there you go, I hit the count button. And it might stay 0 for quite a little bit of time here. But that's counting the number of radon decays that it sees per minute. And what it'll do, there's a little printer that you can attach to this that prints it out hourly. So you could deploy one of these in the house and let it do all the work that you might do by taking a lot of grab samples. So this is taking, in effect, hourly grab samples, because it's going to print out the results every hour. And when you're done, you have the result right off the bat. You don't have to return this device to the laboratory. So this is a continuous radon monitor. And the advantage of a continuous radon monitor, that's a continuous radon gas monitor, is you do get hourly printouts, so you can see the fluctuations that occur during the day, and you do also get an average value when the unit is done after the number of days you leave out. These are not too commonly used, the reason being that they're for doing house measurements, because they're fairly expensive. They're in the thousands of dollars, whereas a charcoal canister or an alpha track measuring device are typically, well, a charcoal canister will typically run you about $15, and an alpha track device costs you a little bit more than that, typically $20, $25, maybe a little bit more. So for doing a singular home, then clearly these kinds of passive devices, including this one, which I'm just going to show you, are the far less expensive ones than this kind of device. So this kind of device is used predominantly, I would say, for diagnostic testing in homes. And finally is the EPERM, or electret. Now in this kind of device, which is just a little chamber like this, typically, what we have in here is this is the detector itself right here, or this is the principal portion of the detector, and the little plastic white, well, it's actually a Teflon surface, is charged up to an electrical charge of about 700 volts when you get it. And it screws into the bottom of this chamber, and all you do is you put it in a place like that, and when you want to activate this unit, you go to your home, the room you want to test, you just lift up the top, and now what happens, the radon gas seeps in here. And when the radon gas explodes, decays, inside this chamber, it will lower the voltage on that plate, on that little Teflon surface that you saw. And the lower the voltage on the Teflon surface, the more the voltage drops, the more radon must have been in this chamber. And this is called an electret measuring device, and the manufacturer's name is EPERM, which I've placed here. And these two can be used from 2 days to many, many months. So those are the principal measuring devices, and it seems like every few months a new measuring device comes out. But principally, these are the major devices that you're going to see. I'd like to leave you with, on this particular issue, the fact that regardless of the device you use, it must be deployed for a minimum of at least 48 hours. Now I want to discuss some of the data that has been produced. In the very beginning, in 1988-89, Dr. Bernard Cohen from the University of Pittsburgh, who was in the forefront of making radon measurements, had shown these particular values to me. I got a hold of this, and they're called, and so I called them the preliminary Cohen survey. It was obviously in the very beginning, because you see the number of measurements is relatively small. The number of measurements that are ongoing now are in the tens of thousands, and so so these numbers are relatively small. But it was an interesting hint, and shows you how easily you can be misled by data. If you look at all of these counties And this is the number of houses measured in these counties. And this is the average radon concentration taken over those houses. And if you looked at all these, and you say, well, which one has the biggest problem? You would say, well, Cumberland County would have the biggest problem. But what's missing in here is the time of year. The Cumberland County measurements were made predominantly in the winter, whereas the other measurements were made predominantly in the summer, or not winter months. Now, in the winter months, the house is closed up more tightly. So the radon gas comes into the house, doesn't get ventilated as much, and the concentration will go up. And the correct conclusion to draw from this data, if I'd given you all the information you needed in the very beginning, is that winter concentrations will be higher, typically, than summer concentrations. And this was one of the first hints that there will be seasonal variations in the radon concentration, and so we should expect other kinds of variations in the radon concentration in a home as well. And I'll summarize some of them for you right here. Of course, what I just mentioned is the top one. And then, of course, I already showed you the hourly variations. I drew that little graph for you of the hourly variations in the radon concentration that occur in a home. And another interesting parameter is that basements are generally higher than first floors by about a factor of 3. This means if you have a radon concentration in a basement of 9, you would expect to have on the first floor a radon concentration of around 3 or 4 or so. And this is a fairly loose rule of thumb, you might say, but it's not unreasonable. And in fact, experimentally, I can show you that that's pretty much the case. It makes sense because here in the northeast United States, more than 95% of the homes have basements. And so the basement has 4 walls and a slab, perhaps, that are all in contact with the ground, and the soil gas can percolate through the cracks in the concrete, etc., and get into the basement. And then that will flow, in many ways, up through into the first floor. But the basement's in much closer contact with the radon than the first floor, and so its concentrations will tend to be higher. And the same thing with the second floor. If you have a second floor, say a colonial-style house, the second floor radon concentration should be less than the first floor, and the first floor less than the basement, and in each case by roughly a factor of 3. Now, of course, I know there are exceptions to this that have been brought to my attention. Suppose you have a house with forced hot air. You're taking air from the basement, you're heating it, you're passing it up into the first floor and into the second floor. In cases like that, you might expect to see second and third floor concentrations, or first and second floor concentrations, to be roughly the same as what you have in the basement. But if you don't have forced hot air, this is typically what you should see. And in fact, if you don't have forced hot air, suppose you have a house that's completely electric, and your basement concentration is 9 and your first floor is 9. I'd be suspect. What the how's it getting to be 9 on the first floor when the basement is only 9? That kind of result would make me want to look at the issue more carefully. So these are some of the trends you should expect to see. Okay? So there are hourly trends, there are seasonal trends, there are actually weather trends as well. If you have a low pressure area pass through your home, for example, when the weather goes bad, oftentimes it's in a low pressure area. That means you've decreased the atmospheric pressure, and so you can have a lot more radon gas coming up. The winds will pick up, and that will actually lower the pressure in the house, and that will have an impact on the radon concentrations in the homes. So there are also meteorological conditions to concern yourself with. I think I've shown you a number of parameters that you'd have to pay attention to. And again, you'll find on the very next page another list of questions that I would like you to work through, and then return to the video at this point. Next, I'd like to discuss with you how we know that it's a health hazard. There's been some debate in the public in the last few years about whether or not radon is in fact a health hazard, and I want to spend a few minutes on this particular issue. We know that high doses of radioactivity, of course, are not good for us, and we know that, as you can see here from this visual, that we have the mortality statistics of atomic bomb survivors. We're all aware that the United States dropped nuclear weapons on Hiroshima and Nagasaki, and we have the data from those two detonations as to the numbers of deaths and protracted radiation sicknesses that have been caused by that. So we know that if you have huge doses of radiation, we know that's not good for you. We also have data from persons treated with radiation therapy. When radiation was first used and became a clever tool in medicine for reducing and destroying tumors, for example, you would fire a radioactive beam or a beam of particles from radioactive material onto a tumor, and you would destroy the tumor. Well, unfortunately, in the very beginning, we were not all as wise as we would like to have been, and the radiation doses were so large that sometimes we destroy the tumor and the patient as well. And that kind of information is also available. We have the information from uranium miners and also other miners who are working deep in the ground, and when you're working in the ground, of course, you have a lot more soil gas in your vicinity and therefore a lot more radon. And we have some information from that. And I admit there are complications to every one of these studies, but all of the data points in the same direction. We also have data from workers who would paint watch dials with radium, which is another radioactive material, radium-laden paint. And if you remember from years ago, I can't remember it from way back, but I have heard that there were watches that would glow in the dark. The hands would glow in the dark. And the reason they would do that is they were laden with radioactive paint, which when it would radioactively decay, would cause the paint material to give off light. And so how do you make a real fine line on the second hands of a watch, for example? Well, you take the paintbrush that you're painting those lines on with, you dip it in your mouth, you lick it a little bit, you put it in the paint, and you draw that real fine line. And what happened was these workers ended up getting tumors and cancers on their lips and tongues. And briefly, I can show you a factory image of a bunch of people. I don't know how well you'll be able to see this, but people who were doing this kind of thing. And you'll notice it's almost all women, and none of them particularly happy, it seems. I don't know if they knew what the issue was that was going on, but there they are painting the dials. Now, those were all pretty high doses, and so in this next visual I'm showing you here, I point out that we know the effects of high doses of radiation. We know that if you put, say, 10,000 units of radiation on 10,000 people, we know that, let's say, 10 of them will come down with cancers. I don't know if those numbers are right, but we know that high concentrations produce significant effects on humans. And if you look at the data in some detail, you'll discover that while we know the effects at high doses, we don't know what exactly is going on at the very low doses. That is, if you expose 10,000 people to 10,000 units of radiation and 10 of them get sick, if you cut the radiation in half, you'll find that only 5 of them get sick. That is, you decrease the radiation by half, by half, by half, and you decrease the effect by half, by half, by half, by half, roughly. And how low can we go with that? Well, here's a graph of some of the data. And I've plotted here excess lung cancer rates and exposures, and these are arbitrary values here just to depict the data. And you'll notice that the data does in fact lie on a straight line, which means as you decrease the exposure, the amount of radiation to which humans are exposed, you're also going to decrease the number of lung cancers due to those exposures. Now, the interesting thing here is the data that we have goes down to only certain values. In fact, goes down to values roughly equivalent to 50 or 60 picocuries per liter. But in many homes, we find concentrations of 4, 5, 6, 7, 8, 9, 10 picocuries per liter. Now, what's happening for them? Do they follow the straight line down to the origin? That is, what should we assume for those people? If the concentration in your home is 10, and our data only goes down to 50, can we assume that at 10 there is still a health hazard, or is there some value below which there is no health hazard? So the question is, what are we doing from here to here? What kinds of assumptions are we going to make? We don't have data, we have to make assumptions. Well, the possibilities are as follows, and there are actually a few more possibilities than what I will depict for you, but I think this covers the important ones. It is possible that if we actually had the data might fall along this kind of path, indicating that there's a threshold. That is, if you had a radon a concentration, say, of 10 picocuries per liter, maybe there's no health risk to that. And in that case, we would say that there's a threshold below which radiation is not hazardous to you. That's a possibility. Now, it's a possibility based on physical grounds, as I will explain now. And that is, humans have evolved in radioactivity and in radiation since the beginning of humans, some few million years ago. And it may be that we've evolved in such a way that low doses of radiation we have somehow become acclimated to, and that there is no risk due to that. For example, reasonable amounts of sunlight don't appear to be a problem. Humans have evolved with sunlight. Reasonable amounts of carbon dioxide are not a problem to humans. Of course, if you breathe only carbon dioxide, you know you're going to die in a matter of a few minutes. But small doses of it don't seem to be a significant hazard. So it may be that small doses of radiation are not a significant hazard. I don't know. And neither does anyone else at this point. So it is possible that there is a threshold. It is also possible, of course, that there is no threshold. It may also be that the data continues to follow along a straight line like this. That is, if you go from, let's suppose this is 50 picocuries per liter. If you go to 25 picocuries per liter, you reduce the lung cancers by half of what it was here. If you go to 12.5, you'd reduce them by another half. It is possible that there is no threshold, that any amount of radiation is hazardous to you. That is a possibility. Well, by gosh, what do we assume in a case like this? Well, the scientific community, to a large degree, has accepted this model as the correct model. And again, it's just an assumption, and it's called the straight line model with no threshold. We simply assume that there is no radiation below which, no radiation concentration below which there is no health hazard. Let me put that in a positive sentence. Any amount of external radiation or any amount of additional radiation is bad for you. That's what this, this curve is indicating. Now, of course, we don't know if that's true. And so you could subscribe to a number of different philosophies in this regard. But clearly it is the prudent assumption to make. If it is true, then we will be taking proper steps. If it turns out to be true some 20 years from now, perhaps we know that there is a threshold, then, well, we'll have taken too many steps, but we will at least have been on the safe side. In any case, the scientific community, to a large degree, there are always those who don't agree, but the scientific community, to a large degree, has accepted this as the correct model to use, the correct guess. In regards to those risks, the EPA has published several tables. This is one of the tables that indicates what the risk is. And this is the table for those people who have never smoked. And let's just take a look at some of these values here. There we go. For example, suppose you're living in a home with 2 picocuries per liter, and you live in that home for a lifetime. Under those assumptions, about 2 people out of 1,000, this is out of 1,000, about 2 people could get lung cancer. Oh, excuse me. I was using the 2 picocurie per liter, gives you 1 person could get lung cancer. If you double the concentration, you'll notice about 2 people could get lung cancer. You pretty much double the risk. If you double it again, you get almost double the number of people. You get to 3 people could get lung cancer, etc., etc. And this is a pretty realistic table. I don't want you to think that representatives of the EPA just sat down and made up some guesses. There are fairly sophisticated calculations that lead to this table. If you're a smoker, the results are roughly 15 times as large. In other words, if you live in a concentration of 2 picocuries per liter and you're a smoker, roughly 15 out of 1,000 of those people, of smokers, would get lung cancer. So you see that smoking increases the health risk for lung cancer by about a factor of 15. There are all kinds of ways to look at risks, and I'm going to show you one last table of risks that are taken from an average value over a number of measurements, over a number of studies by the federal and state governments. Namely, if you take a look at a bunch of government studies, none of them agree with any other study, exactly anyway. But they all have generally the same sense about them. And if you take an average over them, you'll end up with a table like this. Well, if you take an average the way I took it, you'll end up with a table like this. Looking at the number of days of life that you lose due to certain things that exist. For example, the United States has somewhere over 100, I think it's about 110 or 112 nuclear power plants operating in the U.S., and that because of that nuclear power, you lose 4 days of your life. Excuse me, 0.04 days of your life. That's 1 hour. That is, suppose you knew, I don't know how you would know this, I'm not sure you'd want to know this, but suppose you knew that you were going to live to be 70 years old. Exactly. Then, because nuclear power exists in the United States, due to those 112 power plants, you lose an hour of your life. So you're only going to live to 70 years, 70 years minus an hour. So 69 years, et cetera, et cetera, et cetera. 70 years minus an hour. That's what you're going to lose on the average. On an average. Now, some people are going to live much longer than that, some much shorter than that, but on the average, this is the way the estimates break down. Air pollution, because of air pollution in the United States, you lose about 20 days of your life. So because of air pollution, 70 years minus 20 days. Now, of course, if you live in a region where there's not much pollution, and I'm not sure where that would be in the U.S. at this point, but if you live in a region where there's not much pollution, then, of course, this won't have an effect for you. Now, if you live in the cities where there is a lot of pollution, and many of them, then you're likely to lose more than this number of days. But on the average, you're going to lose 20 days of your life. If you live in a radioactive concentration, in this case a radon gas concentration of 1 picocurie per liter, you'll lose about 100 days of your life. So you see, if you're living at the action limit of 4, you're going to lose about 400 days. I'm going to call that a year. You're going to lose about a year of your life, which is the same loss of life as if you smoked 1 cigarette per day. And to a reasonable degree, it is true that you can increase these values exactly linearly for a little bit. In other words, if you double the radon concentration, you'll double the number of days that you lose of your life. If you, and as I pointed out, if you had 4 picocuries per liter, you'd lose about 400 days of your life. Now, you can't extrapolate that out to any arbitrary value. It's true only for values around these numbers that are given here. Obviously, let's suppose you smoke 4 cigarettes a day, you'd lose a year of your life. So does that mean if you smoked 400 cigarettes today, you would die immediately? The answer, obviously, no. And so you can't extrapolate these forever, but you can at least look at them, and they're pretty reasonable handles. And if you want to know what the health risk is due to radon concentration in your home, you can compare it to what the health risk is for smoking. We all seem to have a sense about the health risk of smoking, and so you can use that as a relatively good handle on the issue. Due to car accidents in the United States, the average lifetime loss is about 200 days. Even if you never have an accident, it's an average. If you're 25 pounds overweight, you lose 2 years of your life. And if you're poor, you lose 4 years of your life. And of course, these things are reasonably true. For example, if you're poor, then you don't typically get the same quality of food, the same kind of medical care. I know we'd like to think that that's not the case, or we're working in a direction where that wouldn't be the case, but currently this is true. And you lose those kinds of things. So if you have a home with 4 picocuries per liter, in it, which is costing you about a year of your life, and you're also 25 pounds overweight, and you're poor, you might as well forget about the radon problem. Lose some weight, get a good paying job. Worry about the radon at a much later time. Anyway, these kinds of risk estimates give you some handle, some perspective with which to look at the concentrations of radon that you might find in homes. Well, I hope you found this useful. Thank you very much.